Alright, chapter 5, video 2. So, work has units of energy, right? Newton meter is a joule, right? So if you do work on any object, you're changing the energy of that system, right? You're changing its state, you're changing the amount of energy it has. So I guess we have some experience with energy in, our other science classes, but it's a pretty abstract concept, right? We can't really measure energy unless it's moving in and out of a system, right? So it's very difficult to like say how much energy something has or observe an amount of energy unless it's being transferred, right, into or out of a system. So there are two types of situations, right? There's going to be energy changing in a system, and then there's going to be energy remaining constant. Okay, so kind of like we did with chapter 4, we're going to identify a system, right? And then we can look at all the different sources of energy that's changing the system, right? Transferring energy in, energy leaving. And so these are going to be our types of energy. These are variables. I use slightly different variables, so I'll talk about that as we go through. So we've got two scenarios, right? Either energy of a system is changing or the energy remains constant, right? And so if the energy of a system is remaining constant, that's the law of conservation of energy, okay? Inside a system, it can change to different types of energy, but the total mechanical energy of the system is going to stay constant as long as something isn't putting energy in or taking energy out of the system. And the way we transfer energy into or out of a system is by doing work. All right. So we've got work, which changes the energy of the system. If there is no work done, energy doesn't change, energy is conserved. So those are the basic two scenarios we're gonna deal with for the rest of chapter 5. So let's talk about a certain type of energy. There are many different forms of energy. We're going to focus on two in this course. First one is kinetic energy. Okay, kinetic energy. That's the energy concerned with an object that's moving, right? So if an object's moving, it's got kinetic energy. It's also dependent upon the mass, right? If you have a projectile moving with the velocity, the kinetic energy of the object depends on its velocity and its mass. And we'll define an expression for it later on. You may have, if you took physics in high school, you probably remember what it looks like. But so any object that's moving has kinetic energy. All right. So that means if something's stationary relative to your reference frame, it doesn't have kinetic energy. Our second type is potential energy. We're going to first deal with gravitational potential energy. Potential energy is associated with an object's position within some coordinate system. All right. So it's defined by the system, not just the object, but it's defined by the objects in the system and the reference frame and the coordinate system. Okay. They are, we'll talk more about this later in the semester. They're massive objects. They're exerting gravitational forces on each other. So there's a potential energy associated with how those objects are interacting as well. Okay. So it's a stored energy, right? It's stored inside that system. If you lift an object off of the floor, it's got a potential energy associated with it based on how high it is off the floor. Because when you let go of it, it's going to move with some speed towards the center of the earth, and it's going to have some kinetic energy. So that's the first basic scenario we're going to deal with, is gravitational potential energy being transformed to kinetic energy. And we'll talk about springs later. Again, this is, I think, the second or third time I've mentioned springs without actually formally introducing it, but We'll talk about elastic potential energy or spring potential energy in a couple slides. Alright, so here's our math, right? Here's our, well, I'll show you where these terms come from too. I know, you know, given our situation, I can't really derive expressions the way I normally would, but with these two terms, I'll show you where they come from. So kinetic energy is 1/2 an object's mass times its velocity squared. Right? So it's dependent upon its mass, dependent upon its velocity. There's another term in chapter 6 that's dependent upon both of these two. So there's a relationship between an object's kinetic energy and something else. All right. Then we've got gravitational potential energy, right, which is the force due to gravity on that object, right, mg times y. That's its position, right? So think of this term as kind of like a work, right? Because you've got a force here, you've got an mg, you've got a position, kind of, right? It's written a little differently, but you know, it's got the same units as work, right? And it kind of looks like a work expression, right? A force times a displacement or something, right? If we've got an object in free fall near the surface of the Earth, we're going to say that the total energy doesn't change, all right? So this is K final. This is final kinetic. This is final potential. The right side of the equation is your initial kinetic and your initial potential, okay? So this is saying that all the energy that the object has after some time is the same amount of energy it has at the beginning of the event, right? So the energy is not changed if the object's in free fall. Okay. All right. So here's an example, right? Here's our free fall example. Excuse me. Here's our free fall example. Some object is here at a y initial, right? You're holding an object up here. Maybe you throw it down, right? Maybe you give it an initial velocity. Okay. So at y initial, it's got a kinetic energy and it's got a gravitational potential energy. Okay. It's moving, excuse me, and at some height above the surface of the Earth. So sometime later, it's at a position y final, right? It hasn't hit the surface of the Earth yet, and we'll talk about why I want the surface to be 0. It's at some initial or some final position sometime later. It's still got a final velocity, right? It's accelerating, free fall, you know, force due to gravity. It's got some new velocity, right? So it's got a new kinetic energy, but it also has a new potential, right? Because it is some position, all right? So basically what we're doing here is we're using a kinematics equation to derive our energy terms, right? So this is a kinematics equation we're familiar with in the y direction. This delta y is y final minus y initial. So if you factor this negative 2g across, right? Factor this negative 2g across, you get negative 2g y final plus 2g y initial, right? Because I'm factoring the negative signs. So if I get all the final terms on one side, right? In order to get all the final terms on one side, I'd have to add this plus 2g y final to both sides, right? I can leave this positive 2g y initial on this side, right? So I'm basically getting all my final terms on one side, all my initial terms on the other, all right? But these are units of meter squared per second squared, right? So I want them in terms of Newton meter squared. So I want them to look like kilogram meter per second squared times meters. Okay, so that means every one of these terms I'm going to multiply by the mass of the object. Then I'll be in units of kilograms meter squared per second squared, which is a Newton meter, which is a joule. Okay, so I multiply both sides by m, but I'm also dividing both sides by 2, right? Because I want my terms to match my energy terms. Okay, it's much easier to define gravitational potential energy like this, right? And there are other reasons that are, you know, beyond the scope of this course, but basically I'm just multiplying everything by a constant to make them look like our terms, right? So I use this kinematics equation to show you that this is true. Okay. So the final kinetic plus the final potential equals the initial kinetic plus the initial potential. All right. So there's no external agent doing work on here, right? You're saying to yourself, I disagree, right? The Earth is applying a force on the object, and it's causing a displacement, and it's doing work. Okay, that's true. You disagree. That's fine. We'll talk more about that. So what happens here is we've got an initial potential and initial kinetic. We know the object's in free fall, so the kinetic energy is going to decrease because the velocity increases, right? This velocity vector is smaller than this velocity vector. It's accelerating in the negative y direction. Okay. So as the kinetic energy increases as it's in free fall, the potential decreases. All right. You see this y initial is greater than this y final, right? It's farther away from y equals 0. So you've got a higher potential energy up here and a lower kinetic energy. Down here you've got a higher kinetic energy and a lower gravitational potential energy. All right. So the energy is transformed in this system, but it doesn't leave the system. Right? Total mechanical energy is still conserved in this system. Again, you're saying, I don't know, where's the Earth? Right? The Earth is doing work. I don't agree with you. That's fine. Alright, so let's take an object that we toss up from the ground. So what I'm going to say, my convention, as much as possible, is I want the gravitational potential at the surface, right? The lowest point an object can reach on the Earth is the surface of the Earth, we'll say, right? Assuming you don't dig a hole and bury something, right? So the surface of the Earth, I'm going to say an object has 0 gravitational potential. Why? You set an object on the ground, it doesn't fall towards the center of the Earth. Okay, the surface of the Earth is holding it there. So I'm going to use that as my 0 potential configuration. All right, that's where I'm going to say the gravitational potential of an object is 0. So now you pick it up, you throw it up in the air, you give it an initial kinetic energy. So all the energy it has, now you are doing work, right? You're outside of the system, you come walking over, you pick up this ball, you go, all right, let me throw it. You're an external agent, you're applying a force on this object, and you're displacing it, maybe a little bit just to get it going, right? So it's got all kinetic energy. As it accelerates back towards the center of the Earth, right, it slows down, right? We're a projectile, we're in free fall. We're given an initial kinetic energy. That kinetic energy starts to decrease because the object's slowing down. But it's also moving in the positive y direction, right? So y keeps getting bigger and bigger and bigger until it gets to its max height. So as the kinetic energy is decreasing, the gravitational potential is increasing, right? Because it's getting farther and farther away from the surface of the Earth. Once it gets to its max height, its velocity is 0. That instant when it reaches its max height, its velocity is 0 because it's changing direction. Now all that kinetic energy you gave it has been transferred to potential. Alright, but the total mechanical energy still remains constant. And then it descends, you're in free fall, it descends, and then all that potential gets transferred back to kinetic again until it strikes the ground. And now it still has kinetic energy, right? Remember, this velocity vector is the same as this velocity vector for symmetric free fall. This velocity vector is the same, so it's going to have the same kinetic energy. Remember, kinetic energy and potential energy are scalars, right? So this is v squared. This is a vector squared. So I'm just talking about the scalar, right? I'm talking about the magnitude of the velocity. All right, so the kinetic, it doesn't have negative kinetic energy. It's got a negative velocity, but it doesn't have negative kinetic energy. It just has the same amount it has before. Okay. All right, so I'm taking an example from a textbook. I like this textbook. So we're going to use energy concepts to find the max height of this pebble. All right, so we're in chapter 5. We're going to use energy concepts. Right now you're thinking, I could just do free fall kinematics. It would take less time. I think it'd be easier. That's probably true in this case. But later on we're going to see different types of motion where using energy concepts is going to make our lives easier. Because objects aren't going to follow a straight path. They're going to be losing some energy due to friction. There are going to be all sorts of types of situation where investigating the energy of the system will help us find some physical quantities about the object. So we're looking for max height. It's given an initial velocity, right? But what I'm going to say is this is an isolated system, and I'm going to use this process here. I'm going to use energy concepts to find the max height. All right. So just like this situation here, a pebble is being launched with an initial velocity, we'll say from the surface of the Earth, right? Bob is standing on the surface of the Earth. Okay, so we'll say wherever the pebble is launched from is my zero potential energy position. All right. So Bob gives this pebble an initial kinetic energy of 1/2 mv squared. It doesn't have any gravitational potential because it's near the surface. It gets thrown up in the air. Once it reaches max height, it's going to have all gravitational potential, and it's going to have no kinetic. Similar to the way we handled it with kinematics, right? We set V final equal to 0 to find the max height. So here is my conservation of energy equation. The initial kinetic plus the initial potential equals the final kinetic plus the final potential. So what I'm going to do in future examples is I'm going to write out this equation. I'm going to look at these terms, and then I'm going to look at the situation and see what I can set equal to 0. Okay. So our kinetic energy and our potential energy terms are substituted first, right? These are my final energies. These are my initial energies. What can go to 0? This is the initial energy. I know the initial potential is 0, right? Or sorry, over here. It's got final on this side, initial on this side. I switch that a lot. I like initial on this side, final on this side. Symmetric property of equality, it doesn't matter. But so this is the initial position. This thing right here goes to 0, right? Y naught is 0. So this initial gravitational potential energy term is 0. At max height, the velocity is 0. So this K1, this final kinetic energy, goes to 0. So that means the initial, or the final potential energy, is equal to the initial kinetic energy. I'll say that again. The initial kinetic energy is equal to the final potential. And so down here, we can simplify the equation and say the initial kinetic energy, 1/2 mv naught squared, equals the final potential energy, mgy1 squared. So now I can solve for max height. Y1 is the object's position at max height. Notice the masses go away. I got a mass on either side. So all I got to do is solve for y1, and that's divide both sides by g. I get v naught squared over 2g. If you set this up using free fall kinematics, this would be the expression for your max height. So they would agree. Now I can plug my values in. I've got my initial velocity. I know what g is, and I can find the max height. All right. So again, mass has always kind of gone away with kinematics equations, right? We never had to deal with the mass, all right? And so the same thing happened here. Okay. So let's talk about why I want the surface of the Earth to be 0. All right. This is the system that I find to be most convenient. Again, gravitational potential energy is defined by your coordinate system. Okay, I'm not concerned as much with an object's gravitational potential energy as I am with how it changes. Okay, I'm concerned with how energy changes, not necessarily the state of an object's energy. Right, I'm concerned with how it's transferred. All right, so I like to use the Earth's surface. We'll talk more about springs. This should be unstretched. Sorry, that's a typo. That should be unstretched. And again, when I introduce springs, I'll talk about where I want the spring potential to be 0. Okay, I like it to be the Earth's surface because an object, once it hits the Earth's surface, it's not going to move. Right? Nobody's going to let go of an object on the surface of the Earth and have the object in free fall. All right. So I like to pick the Earth's surface whenever possible, and then your coordinate system has to be constant throughout the problem. All right, and what that means is I want to be amber. All right, I want to be amber. Through all my problems, I like amber more than I like Bill. So let's talk about amber and Bill. There's a rock in the air, right? Let's say there's a third person holding a rock here, and they're going to drop it. Amber says, I want the ground to be zero potential. I want the ground to be zero potential. So that means this 1 kilogram rock has a gravitational potential of 1 kilogram times 9.8 meters per second squared times positive 1 meters. This energy has positive 9.8 joules. When this third person lets go of it, Amber's going to say initial gravitational potential is 9.8 joules, final gravitational potential is 0 joules because it hits the surface of the Earth. That's Amber. Now Bill does something different. Bill says, I'm going to pick right here to be 0. I'm going to pick the object's initial position to be 0 meters. So it's got an initial potential energy of 0 joules. When this third person drops the rock, it's going to fall, and it's going to be at a position, according to Bill, negative 1 meters. So its initial gravitational potential, according to Bill, is 0 joules. Its final gravitational potential is going to be 1 kilogram times 9.8 meters per second squared times negative 1 meters. So Bill's final, or the final potential according to Bill, is negative 9.8 joules. Now let's take the final minus initial in both cases. For Amber, 0 joules minus 9.8 joules is negative 9.8 joules. So this object changes, has a change of potential energy of negative 9.8 joules according to Amber. We look at the change of potential according to Bill. The final potential is negative 9.8 joules minus 0 joules. So regardless of their coordinate system, they see the rock's potential change by the same amount. They both see a negative change in gravitational potential. So you can choose your coordinate system. Again, I do like Amber. It's more convenient, right? Picking the lowest point that the object can reach as 0 is the best bet. So the gravitational potential of any object above that is going to be positive. Okay, that's my preference. I like to be Amber. That's how I handle all my problems. Again, you can do it differently, but as long as you can calculate the same delta U, you'll be okay. Alright, so here's Amber, here's Bill again. We've got a falling rock, right? So we are looking for the speed just before it hits the ground. Just before it hits the ground. We're still going to stick with these two different coordinate systems. The rock is going to be released from rest, right? So it's got an initial kinetic energy of 0 for both people, right? Kinetic energy is 1/2 mv squared. If you're released from rest, velocity is 0. Right? So this object has no kinetic energy according to Amber and Bill when it's released. So we've got, for Amber, we've got 0 velocity, an initial position of positive 1 meters. When it reaches the ground, it's at 0 meters. We're looking for V final. Okay, same thing with Bill. We're looking for V final, but the coordinates have changed, right? The initial and the final position have changed. So the total mechanical energy is conserved. Again, total mechanical energy is conserved. So that means the final energies are equal to the initial energies. In both cases, K initial is 0, right? Because the rock is released from rest. So this term can go away, right? What we're doing here is we're taking K final. We're going to solve for K final because we're looking for the final velocity. Now, in both cases, K final is equal to UG initial minus UG final. UG initial minus UG final. So it's different from delta U, right? It's initial minus final when we solve this. All right. Well, what they do here is they factor out a negative sign. Okay. So UG initial minus UG final is the same as negative the quantity UG final minus UG initial. So the final kinetic energy is equal to the negative change in potential energy. So the final kinetic energy is equal to the negative change in potential energy in this case. But Amber and Bill both have different values for their final and their initial kinetic energy. So calculating delta U for Amber, we've got a negative 9.8 joules. We've got 0 joules minus 9.8 joules for Amber because the surface is 0. 0 joules at the surface. All right, so Amber gets negative 9.8 joules. Bill, his coordinate system is different. So his final potential energy was negative 9.8 joules, right? Because the surface was negative 1 meter below, negative 1 meters from his initial gravitational potential position. So Bill's change in potential is negative 9.8 joules minus 0 joules. Again, just like we talked about before, their coordinate systems are different, but they have the same change in potential. So let's solve this. 1/2 mv final squared equals negative delta U. Let's solve this for v final. Multiply both sides by 2, divide both sides by the mass, take the square root of both sides. We get v final is negative 2 delta U over m, the square root of all that. All right. Panicking here a little bit, right? Getting a little worried. I got a negative sign. But Amber and Bill both calculated their change in potential the same way, and they got a negative change in potential. So these negative signs are going to cancel out. I'm going to have a positive term. I feel better, and I get a final velocity of 4.4 meters per second. For both Amber and Bill, again, I'm more concerned with the change in potential than the individual potentials at different positions in their coordinate system. Okay. So for fun, you can use kinematics, right? You use free fall kinematics and verify v final, right? You can verify that final velocity using kinematics, okay? All right, so let's talk about springs. I know I've been putting this off for a little while here. Let's talk about springs, okay? I've got an unstretched spring, okay? I've got a spring. It's an ideal spring, we'll call it. And I'll talk about why we call it an ideal spring. It's unstretched, okay? So I'm going to say this is x equals 0 or s equals 0. Right? This is the unstretched position. And if I go back, I talked about it a couple minutes ago. Okay, my typo here. Unstretched spring position. All right. So I'm going to say the energy of this system is 0 right now. All right. So this is x equals 0. This is what we call the equilibrium position. The equilibrium position. Nothing is pushing on this. Nothing is pulling on it. It's in equilibrium. All right. So grab the spring and pull it in the positive x direction. Right. You pull a spring in the positive x direction. That spring doesn't want to do what you're doing to it. Okay. So it's going to pull back. Right. It's going to pull back. And the farther you pull it away from x equals 0, the stronger it gets, right? The harder it is to pull it farther away. So the force you're feeling on that spring gets stronger and stronger the farther you are away from this. So it's not a constant force, right? It's not a constant force. This is what we call the restoring force, okay? It's being produced by the spring on you, right? Because it wants to get back to its equilibrium position. So that's the restoring force. That's the Hooke's law force, the spring force. Do the same thing. If you push in the negative x direction, the spring is pushing back on you. Right? The spring is pushing back on you in the positive x direction. So these restoring forces are opposite the direction of the spring's displacement, the direction that the spring is being stretched. This restoring force opposes that displacement. All right, and again, it's changing with the displacement. The farther you push that spring in, the more it wants to push back and get to equilibrium. Okay, so it's not a constant, right? It's not a constant force. If you see by this graph, it's not a straight line, right? You see it changes the farther you are away from delta, or from the equilibrium position, excuse me. So we have to know the displacement, right? We have to know how far the spring is stretched to find out what that restoring force is. All right, and here's my Hooke's law. The spring force, this is the force by the spring on you, is negative k delta s. It's proportional to the displacement. It's directly proportional to how far you stretch it in either direction. This negative sign is here because this spring force opposes the direction of delta S. Right? Delta S is in that direction, the spring is in the opposite direction. Delta S is negative here, restoring force is positive. All right? So it's directly proportional to the displacement, and it's opposite in direction. K is our spring constant. All right? This is a constant K, which will either be given or you'll have to solve for, something like that, but it's a constant. It's a property of the spring. All right? Think of it as like the stretchiness. Okay? The larger this number is, the greater this restoring force is going to be. See how it's direct proportionality again? The stronger this is, the stiffer the spring is. Okay? The spring is more difficult to stretch or compress. All right? So the higher the spring constant, the higher the restoring force. All right? So there's my Hooke's law formula. Okay? This is our first force that has not been constant. Right? Every other force up to this point, except for like the work graphs, has been constant. All right. So let's talk about spring potential energy. Spring potential energy. Again, this is a derivation that I usually reserve for class. It also uses calculus, which isn't necessary for this course, but I like to thoroughly derive expressions whenever possible. But this comes from calculus, so we're going to forego that for the time being. I'm going to say that this is an isolated system too. Again, you're not going to agree, probably because you're going to view the spring as an external agent doing work on this ball. I get it, just like with Earth. But I'm going to say this system is isolated. So the total mechanical energy is conserved again. Right? Initial kinetic plus initial potential is final kinetic plus final potential. So what potential energy is inside this spring? Take this object, push the spring in, there's stored energy is in this spring. How do I know that? Because if I let go of it, this is going to move. Right? The spring is going to push this object, and it's going to be moving when it gets to this point, and then it's going to leave the spring. It's going to have some kinetic energy. So there's got to be some energy stored inside this spring that gets converted to kinetic. Okay? And we call that spring potential or elastic potential energy. So again, it's proportional to the how much the spring is compressed or stretched. Right? This X is my new delta S. All right, so this X is the displacement of the spring. K is the spring constant, so the spring potential is 1/2 K delta X squared. So if we know the spring constant and we know how much the spring is stretched or compressed, we know the spring potential. Now the difference here is, for Hooke's law, this could be positive or negative. Right? You could stretch a spring, you could compress a spring. But here, it's a scalar. Okay, it's a vector squared, it's a displacement squared. So potential energy, spring potential energy, is also a scalar. All right. So basically this is just a new potential energy term we have to account for if a spring is in our system. All right. So we're storing potential energy inside of a spring that when we let go of it, it's transformed into kinetic energy. All right. So here's why we use energy. Since the force is not constant, on this object, the acceleration won't be constant either when we let go of it. So it will accelerate, but the acceleration isn't a constant value. All those kinematics equations that have acceleration in it depend upon acceleration being constant. Okay. In this case, acceleration is a function of time and position. So our kinematics equations won't work. So we have to use conservation of energy to analyze the motion of the object. Alright, so we've got two situations, right, from now on. From two situations how we're going to handle energy problems. We've got our first equation and our second equation. We've been dealing with our second equation up to this point. Alright. So I'm going to talk about those two situations that we don't agree with. We may agree with or we may not agree with. And that is the Earth doing work on an object and a spring doing work on an object. I've been using this equation the whole time. This equation is used when there is no work being done by a non-conservative force. So why am I allowed to use this, right? And why am I saying that the earth and the spring are not doing work on the object? Because when I define my system, the earth is part of my system and the spring is part of my system. Just like we use that system method to solve Newton's second law problems, I'm doing the same thing here. The gravitational force and the spring force are conservative forces. Okay, this lowercase nc means non-conservative. We talked about conservative and non-conservative forces. So any work inside of a system done by a conservative force doesn't change the energy of the system. So the earth and the spring get included into my system so that I can use conservation of energy. Right? It makes my life easier because I don't have to account for any non-conservative forces. Sorry. That's why I neglect air resistance. We haven't dealt with any friction problems. So energy is conserved when the only forces acting on the object are spring forces or gravitational forces. The total mechanical energy of the system doesn't change. So just keep that in mind. Make the earth part of your system, make the spring part of your system. We don't have to concern ourselves with the work that something inside the system is doing on another object. Okay. So hopefully now you agree with me that this helps us, right? Keep the earth in your system, keep the spring in your system. Okay. And if you notice this equation, right? If I set this equal to 0, right? If I set this equal to 0 and I take all my initial terms, put them on one side, all my final terms on the other, I get this equation. Right? So this is my work energy theorem. This is work done by a non-conservative force changes the total mechanical energy of the system. Notice this is delta K, this is delta gravitational potential, this is delta spring potential, final minus initial. Now some textbooks are using PE for potential energy and KE for kinetic energy. Some textbooks have been using, let's see if I can find them, here we go. Some textbooks use K for kinetic and U for potential. Alright, so just be comfortable. I personally don't care what variables you use. I like K and U. Some textbooks, I think your version of Survey uses KE and PE. Okay, so just whichever one you're comfortable with is fine. Just make sure you're consistent, and when I use U, just make sure you recognize I'm talking about potential energy. Alright? So this is my work energy theorem. This says work by a non-conservative force is going to change the energy of the system. If this is 0, this tells me delta, delta, delta. My change in my total mechanical energy is 0. That means energy is conserved. So basically this equation is a modification to this if there are no non-conservative forces doing work on the system. And basically the only non-conservative force we're going to be dealing with is friction. So if there's friction in the system, we use this. If there's no friction in the system, we use this, because total mechanical energy is conserved. Alright, so let me do one mechanical energy problem. I'm getting up there on the time, so I'll do one energy problem, upload it, try and keep it as short as I can, and then we'll start with another one. So this looks like it could be a kinematics problem. Excuse me. This looks like it could be a kinematics problem. But the surface is curved. Right? The surface is curved, so this person on a sled is not following linear motion. All right. So the acceleration of this person on a sled is not going to be constant. Okay, because it's gravity that's going to be applying a force, but the force due to gravity that's causing it to slide down is not going to be constant. It's going to be dependent upon theta. But as this person slides down this curved surface, theta changes, so force changes, acceleration changes. So we got to use energy concepts to find this person's speed at the bottom of the hill. So the person is starting with an initial velocity, so I know it has an initial kinetic energy. It also has an initial height of 5 meters. I'm an amber, right? I like to be an amber, so down here is where I'm going to say the sled rider has an initial potential of 0. Up here, it's got an initial potential of mg times y. Down here, potential is 0. But it also has kinetic, so I have to account for the initial kinetic energy of the sled rider. Okay? So, these are my initial energy terms. Sled rider has an initial kinetic, 1/2 mv naught squared, and an initial potential, mg y naught. And then it's got a final kinetic, 1/2 mv1 squared, and a final potential, mgy1. So the initial position is 5 meters, the initial speed is 2 meters per second, the final position is 0 meters, we're looking for the final speed. The surface is frictionless. Okay, I should mention that. If I don't mention friction, then the surface is frictionless. All right, if friction is not mentioned in the problem, then the surface is frictionless. If friction is mentioned in the problem, or if friction is applicable in the problem, then something will be in there to mention it, right? It'll say the surface is rough, or it'll give the coefficient of friction, something like that. It'll give you a hint to let you know that that friction is doing work on the system. But we're going to say friction. There's no friction, so total mechanical energy is conserved. So initial kinetic plus initial potential is final kinetic plus final potential. I cross this term out, set it equal to 0. Why? Because I'm an amber, y1 is 0 meters. At the bottom of the hill, the sled has 0 potential. So that term goes away, right? I don't want to move any terms around that I don't have to. So I can set that equal to 0 first. I'm looking for V1. So 1/2 mv1 squared is 1/2 mv naught squared plus mg y naught. Alright, so this is the initial energy of the system. So this makes sense, right? Mechanical energy is conserved. The final kinetic at the bottom of the hill has to equal the total energy the object had when it was at the top of the hill. Now it's algebra time. We solve for V1. Multiply both sides by 2. Divide both sides by the mass. Okay. This 2 and the 1/2 go away, but there is no 1/2 over here. So I'm going to have a 2 here when I distribute this 2. It's going to cancel out the 1/2 here. I'm going to have a 2 here. This mass cancels with the masses over here. Again, mass is irrelevant in this case when we're solving for this final quantity. Alright, so V1 squared. This looks very familiar, right? You'll see that happen sometimes. When we use our energy concepts, they'll kind of, when we do our simplification, we're on our way to solving, we'll kind of stumble upon something that looks like a kinematics equation. Doesn't necessarily mean we can use kinematics all the time. Again, the acceleration isn't constant, so kinematics equations aren't always applicable. Solve for V1, take the square root of both sides. I can plug everything in. Remember, y naught is positive 5 meters. The initial position was at the top of the hill because I'm an amber. Alright, plug everything in, and I get a final velocity of 10.1 meters per second. So I'm not asking for the magnitude and direction, right? You could probably deduce by the picture what direction the object is traveling in. More often than not, I'm going to use the word speed, right? I'm going to use the word speed in the problem because I'm not necessarily concerned with the vector properties anymore, right? I'm just concerned with energy. So I'm only concerned with the speed of the object. All right. So this next problem is a doozy. I'm gonna stop this. This is a pretty involved problem, so I'm gonna stop the video, upload it, and then get started on this problem because the next couple problems get pretty involved. So I want to devote a video just to solving problems. Okay. All right. Hope everything's going well. Again, please feel free. Email me any questions. Zoom, whatever you want to do. I got office hours. Check the syllabus. All right. Have a good one. See ya.